Welcome back. We're going to start our next rule on the chain rule. Okay, so we've talked about the power rule when you have the sum and difference of powers. We've done trig derivatives, the six trig functions, being able to find the derivative of those. We've done e and ln, all right? The derivative of e to the x is e to the x. The derivative of ln of x is 1 over x. We've also done some rules as product rule and the quotient rule. Okay, so looking at a function, whether you look at it and you see it as the sum and difference of powers, the sum and difference of powers and trigs, a product, or a quotient, that determines the rule you have to start with. So our next rule is going to be the chain rule. And the chain rule gets used when you have a composition of functions. Okay, so that's not a product or a quotient, but a composition is when there's a function inside of another function. Okay, so that's when the chain rule is going to get applied. So let's state what the chain rule is, and then we'll look at some examples. So the derivative of a composition. So you have to identify the function as being a composition. That means that there's some function inside of another. It could be a trig function that's inside of a power. It could be a power inside of a trig. There's a lot of different ways it could be written. So this is how we would write it. So our d dx, if we took the derivative of a composition. So this does not say f of x times g of x. That would be our product rule. This says f of g of x. So there's some function of x inside of another function. All right. So the rule is we take the derivative of the outer function first. So f prime, we keep the g of x inside. We don't take the derivative of it, but then we multiply by the derivative of g of x. All right, so depending on which function's inside and which one's outside, the outer function we take the derivative of first, keep what's inside, and then multiply by the derivative of the inside. All right, and this is a product. So where product rule is the sum, right? The derivative of u times v was u dv plus v du. Okay, here when you're doing chain rule, you multiply. So let's take a look at some examples, and maybe some examples that actually you don't need to use chain rule for. Okay, so for this one, so looking at example number one. Number one is actually written as a quotient. All right, so we could use our quotient rule, which is low d high minus high d low over the square of what's below. Or we could also rewrite this function. We can't split it up as the sum and difference of powers, but we could write it as a composition. So if you did write it as a composition, it would be this function. Y equals the quantity 2x plus 3 raised to the negative 1. Now, we're not allowed to distribute this negative 1. That's not how powers work when you have addition. So we can't use sum and difference of powers. But now we have a function, 2x plus 3, inside of another function. That function would have been x to the negative 1. So this is written as a composition, which means chain rule can apply. So the outer function is this power to the negative 1 power, so that would be our f. So we have to take the derivative of that power first. So that would be a power rule. Then the inner function is also the sum and difference of powers, and that would be our g of x, and that would be what we take the derivative of last. So the first thing we're going to do is take our negative 1, multiply it out in front, subtract 1 from the exponent, then multiply by the derivative of the inside. All right. So the f prime is the power rule with the negative 1 exponent, so we multiplied the negative 1 out in front, and then subtracted 1 from the exponent to get negative 2, but we kept what was inside. That was our g of x. And then at the end, you multiply by the derivative of 2x plus 3, which is just 2. Now, this is our correct derivative, but it's nice to rewrite it using positive exponents. So if we wanted to rewrite the final derivative, the negative 1 and the times 2 could go on top, and then the bottom, we're going to move the 2x plus 3 squared on the bottom to make it have a positive exponent. We're going to use the derivative for a lot of application problems, so being able to simplify it first is going to be beneficial. So even though this is a correct answer, most of the time we're not going to be just finding derivatives, we're going to be using them. So being able to rewrite them is going to be helpful. All right, so let's take a look at the next example. So the next example, f of x equals cosine of 2x. This is not a product. Cosine is not a number. We're not multiplying cosine times 2x. We're putting 2x inside of cosine of x. All right. So we've got our outer function, which is cosine, and our inner function, which is 2x, and we're going to do our chain rule. So derivative of cosine is negative sine. We're going to keep what's inside, which is the 2x, and then we're going to multiply by that derivative. So that's our final answer here. So we get negative sine of 2x, and then we multiply by the 2. Now keep in mind this 2, we're multiplying it times the negative sine of 2x. So we're not multiplying it by the 2x. So you can't make that 4x. That would be incorrect. This 2x is untouchable. You can't perform operations with it since it's inside the trig function. All we can do is just move the 2 out in front with the negative sign. And that would be our final simplified answer. Okay. Negative 2 sine of 2x. And then for our last example, we've got the square root of 5x squared minus 7x plus 1. And again, you're not allowed to just take the square root of each term when you have addition and subtraction. Just like up here, we couldn't distribute the negative 1 when we had addition. So we could write this as a function being raised to a power. So square root is 1/2 exponent. So 5x squared minus 7x plus 1 to the 1/2. And now we've got a very similar situation that we had in number 1. So we're going to take the derivative of the outer function first. That would be this power rule. And then multiply by the derivative of the inside function, which is also a power rule. So we're going to bring the 1/2 out in front and then subtract 1 from the exponent to get negative 1/2. Keep what's inside, keep the original function inside, and then we multiply by the derivative of the inside, which is another power rule. Derivative of 5x squared minus 7x plus 1 is just 10x minus 7. So now if we want to simplify this and rewrite it with positive exponents, anything with a positive exponent stays on top, anything with a negative moves to the bottom. So the 10x minus 7 is going to stay on top with this 1, and the 5x squared minus 7x plus 1 to the negative 1/2, we're going to move that to the bottom with the 2. And this would be our final simplified answer. If you want to rewrite it as the square root, you can do that as well, or you can just keep the 1/2 power there. All right, the 2 is not being raised to the 1/2 power, so that's why you need the parentheses there. All right, and that would be our final simplified first derivative. So let's look at some more examples where we might have to use the chain rule. So here we've got 2x plus 3 squared inside of a cube root. So remember, we're not allowed to distribute exponents or radicals when we have addition or subtraction, but we could rewrite this as a power. Cube root and squared is the same as 2/3. And notice how I'm keeping everything labeled. So since I haven't taken the derivative yet, the original function was y equals. This function is still y equals. Make sure you're labeling each expression you write so you know what's the original function and what's the derivative, or even the second derivative when we get there. Okay, so now we would look at this and say this is a composition. This is not a product or a quotient or the sum and difference of powers. This is a composition, so we have to use the chain rule. We're not allowed to distribute this exponent. Don't do that. It's not going to equal this function. But we can use our chain rule. So the outer function is this 2/3 power. So we're going to do our power rule. We're going to multiply the 2/3 out in front. If there was any number out in front here, we would multiply by it, but there's not. There's just a 1 here. So we're going to multiply the 2/3 out in front and then subtract 1 from the exponent, which will give us negative 1/3. Then we multiply by the derivative of the inside, which would be our 2. So you bring the 2/3 out in front, subtract 1 from the exponent, keep what's inside, then multiply by the derivative of the inside. And notice how we're calling this now y prime. You could also call it dy dx, all right, if you wanted to. And now we're going to simplify our final answer. So anything with a positive exponent is going to go on the top of the fraction. Anything with a negative exponent is going to go on the bottom. So this 2 times 2 can go on top. And this 2x plus 3 to the negative 1/3, we're going to move it to the bottom with this 3. And the exponent becomes positive. All right, so we end up with a 4 on top. The 3 stays factored out, and the 2x plus 3 is being raised to the positive 1/3. If you wanted to put cube root of, you could do that as well. All right, that would be our final simplified first derivative. Okay, so let's take a look at this one. So now we've got our radicals, we've got it on the bottom, and we want to try to simplify. So technically, looking at this problem, it is written as a quotient. So if you were going to leave it like this, you'd actually have to use your quotient rule. But we could rewrite this because the top doesn't have an x, it's just considered a coefficient. And we could rewrite the square root of 3x squared plus 4 on the bottom as a negative exponent. So this function is called f of x, so I'm still going to call it f of x, negative 12. Now, if we want to move the 3x squared plus 4 up to the top, we just have to write it with the negative exponent. And now this is written as a composition. Right. You might say, well, it's a product, but since this is not a function of x, you don't need to use product rule. This is just acting as a coefficient, so it just goes along for the ride. The 3x squared plus 4 to the negative 1/2, that's our composition. So this is our outer function. So we're going to take the derivative of the power first. So negative 1/2, we're going to multiply it out in front to get positive 6. Then subtract 1 from this exponent, which should give us negative 3/2. Then multiply by the derivative of the inside, which will be 6x plus 0, that can just be our 6x. So we multiplied the exponent out in front, subtracted 1 from the exponent to get negative 3/2, kept what was inside, and then multiplied by the derivative of the inside. Now we're going to simplify our derivative by putting any positive exponents on top. So the 6x and the 6 can get multiplied and go on top. The 3x squared plus 4 to the negative 3/2, we're going to put on the bottom, and it becomes positive 3/2. Notice how each expression is labeled: f of x, f prime of x, f prime of x. All right, so that would be our final simplified derivative. And now let's look at our last example. The last example is a composition, but it's actually going to be a composition of 3 functions. So I'm going to rewrite this using parentheses so I can see which one's my outer functions. So this cubed, when the cubed is here, that implies that the entire sine of 5x is being cubed. And the reason why they don't write it like that is because there tends to be a lot of parentheses. They shorthand it and created this notation so that they didn't have to write all the parentheses here. So we're not cubing the 5x, we're cubing the sine of 5x. So our outer function here is cubed, then we have our sine, and then we have our 5x. So this is a triple composition. But all you have to do is still use your chain rule. You take the outer derivative first, keep what's inside. Then multiply by the next derivative, keep what's inside, and then multiply by the last derivative. So the first function we're going to take the derivative of is this cube, which is a power rule. So we're going to move the 3 out in front and then subtract 1 from this exponent. So we're going to square the sine of 5x. Then we're going to multiply by the derivative of sine, which is cosine, keep what's inside 5x, and then multiply by the derivative of 5x. So that will give us this. So our power rule is right here. So we brought down the 3, kept what was inside, subtracted 1. Then we multiplied by the derivative of sine of 5x. So that was cosine, keep what's inside, which was 5x. Then multiply by the derivative of the 5x, which is 5. Since all of these are being multiplied, we're just going to put our coefficient out in front. So our final coefficient would be the 5 times 3. And again, notice how we're labeling this g prime. So we end up with the 15. Since the sine of 5x is being squared, we can move the squared back here. We've got our 5x and then times cosine of 5x. All right, remember, these 5x's are untouchable. You can't perform operations with them since they're inside the trig function. But that would be our final simplified derivative. So for the homework, when you go through the worksheet, look at each problem and decide what rule you have to start with. If your problem can be written as the sum and difference of powers or trigs, you can just take the derivative of each piece. If your original problem is written as a product of 2 functions of x, you have to start with product rule. If your original function is written as the quotient of 2 functions of x, then you have to use quotient rule. And if your original function can be written as a composition of functions, then you're going to use your chain rule.